Q adjoin beta over Q, right? Using the theorem again, or the corollary, whatever you want to. But you tell me what's going on here. This is 2, right? This is 3. This is some n greater than or equal to 1. So this word right here, suppose Q adjoin root 2 has a 0. You know? Right, no, so yes, in fact, there is no, so in other words, there is no 0 for x cubed minus 2 in Q adjoin root 2. So let me just, conclusion, therefore, P of x equals to x cubed minus 2 has no 0 in Q adjoin square root of 2. Which is kind of neat because that's a cubic polynomial, right? It doesn't have a 0. Therefore, by our earlier theorem, it's irreducible. So this shows you that x cubed minus 2 is irreducible over Q adjoin the square root of 2. Most of our toys, right, about irreducibility concern irreducibility over rational numbers, right? But we've just proved irreducibility over that extension field. That's a sneaky new trick, okay? Which we're not going to really explore much in this course. But if you go on to study Galois theory, this is like one of those basic calculations you use over and over again. So this kind of logic. Alrighty. So example 5 then, I suppose. Here I consider Q adjoin the square root of 2. That field extended further by the cube root of 2. All right. So what would that look like? So building off my example 4, we just learned that x cubed minus 2 is irreducible, right? And by the way, notice that x cubed minus 2 has the, that is the irreducible. If I look at the cube root of 2 over, well, apparently over Q adjoin square root of 2, well, that's equal to x cubed minus 2. Incidentally, that's still true if I replace, it's also true, mind you, that irreducible polynomial for the cube root of 2 over the rationals, it's still x cubed minus 2. So, but this comment is more relevant for what I'm about to write because, so I know that this is an element of degree 3 over that field, which means that if I call this thing alpha for a second, just to kind of demystify it for a sec. So a plus b alpha plus c alpha squared, such that a, b, c are in Q adjoin square root of 2 by our theory. Because that alpha is a degree 3 element over Q adjoin root 2. So I take a Q adjoin root 2 linear combination of that to get an arbitrary element of this extension field. And so what does that actually look like? So A has the form A1 plus let's say a2 root 2, all right? And then b has the form b1 plus b2 root 2, all times alpha. What's alpha? It's the cube root of 2, and then plus c1 plus c2 root 2 times the cube root of 2. So this is what it looks like in gory detail. Here, a1, a2, b1, b2, c1, c2 are elements of the rational numbers. And so, just to, in gory detail here, a1 plus a2, 2 to the 1/2, plus b1, 2 to the 1/3, plus b2, what's a half plus a third? It's a 5/6. 2 to the 5/6 power, plus c1, 2 to the 1/3 power, plus c2, 2 to the, what's, wait a minute. Oh, you know what I missed? I missed something here. That was supposed to be alpha squared, right? Alpha squared. I forgot my square. Right there. And that makes this a 2/3. So what's 2/3 plus 1/2? 7/6, right? I'm tired of writing it. Okay. Rational coefficients. So that's what this extension field looks like, and you can readily see that, in fact, it's 6-dimensional, right? This is a 6-dimensional extension field over the rational numbers, and the basis for it is like 1, 2 to the 1/2, 2 to the 1/3, 2 to the 5/6, 2 to the 2/3, 2 to the 7/6. So that's kind of a neat example. Ooh. Oh. Oh, yeah. That's very low-hanging fruit. Why can't I pick it? So you check it out. These are all what? Can you rewrite these? This is what? 1/2 is actually 3/6, right? 1/3 is actually 2/6, right? All sixths, 4/6. You could rewrite that as 2c2 to the 1/6. In other words, if we let this is really the same as q adjoin the 6th root of 2. Because, by the way, x to the 6th minus 2 is irreducible for what it's worth over q by Eisenstein with p equals 2. And in fact, that simple extension is this field. So, by the way, another notation here, q, so like if you do q adjoin square root of 2 and then the cube root of 2, you can prove that this, okay, so the smallest field, which includes the rational numbers, the square root of 2, and the cube root of 2, is exactly the field we're studying here. This can be pretty easily proved. So this is equal to that. And what we're showing, what I've just argued here, is that is in fact q adjoin the square root of the 6th root of 2. So that means that this is actually a simple field over q because it is an extension by just one element. It's not obvious at the start of this example that it was an extension by one element, but after this calculation, we found, aha, well, the 6th root of 2 is actually, adjoining that one element automatically gets all of this stuff, and then 2 and all of that stuff, all right? Now, there's a theorem. Well, there's a couple theorems I should mention. Theorem, and this one I don't have proof for, but if E is algebraic over F, then there exists finite number of elements alpha 1, alpha 2 to alpha n in E such that E is equal to the extension of F by alpha 1, alpha 2, alpha n. All right. In other words, if and only if E is a finite extension. All right. So I don't have a proof of that, but you can look at a book called Fraley, page 286, which I have a copy of somewhere in my office if you're interested. And then the last theorem that I tell you in the notes is the primitive element theorem due to Steinne in 1910. And what he says is that if we have a field, all right, of characteristic 0, all right, characteristic 0, and E is equal to F of adjoining alpha and beta, then there exists gamma in E such that E is equal to F adjoining gamma. In other words, over characteristic 0 field, we can always rewrite a, well, in principle, we can rewrite an extension by 2 elements as an extension just by 1 element, as a so-called simple extension. Now, I asked you the question last class, right? Remember? So, like example 6 is actually from last class. I mentioned we could look at Q adjoin square root of 2 and the square root of 3. That's a little bit different than my example 5, right? Now, this is Steinne's theorem. He says that this is equal to Q adjoin some particular thing, right? So if we can figure out that particular thing, we can end class. What do you think it is? Yeah, I started by trying.
We asked the same.
Yes.
Same one.
We asked this question last time, we couldn't do it. And the reason we couldn't do it last time is because I multiplied them. That's not the way to go. Instead, try adding them. So check this out. So if I do square root of 2 plus the square root of 3, all right, then that's definitely an element of this, right, to start with. But what's the reciprocal? Well, you know how to do it. Right? Rationalize denominator. And what's that give us? 2, 3. So we get square root of 3 minus the square root of 2. So what good does that do you? Well, the thing is, if my gamma is this, right, then if you look at gamma plus 1 over gamma, what do we got? right, the root 2's cancel, right? So we get twice the root 3, right? And if you look at gamma minus 1 over gamma, what do you get? Then the root 3's cancel, and you get 2 root 2. So, more to the point, the square root of 3 is equal to 1/2 of gamma plus 1 over gamma. And the square root of 2 is equal to 1/2 of gamma minus 1 over gamma. In other words, the square root of 3 and the square root of 2 will be in the extension of Q adjoin gamma. See, because the field, which includes Q and gamma, in a field, you definitely have 1 over gamma, and you can definitely add things together in the field and still be in the field, right? This is the rules of a field. The sum of two things in the field is again in the field. It's certainly a ring before it's a field. A half is in there because we're allowed to do rational multiples, right? This is Q. So all of this is allowed in there, and this shows that root 2 and root 3 are in that. So that implies that Q adjoin square root of 2 comma square root of 3 is a subset of Q adjoin gamma. Because anything I can build with root 2 and root 3 is in here. And but also these are vector spaces, right? So how can I say this? Oh, rats. I have that subset. Is the other subset obvious? Well, if I add these two equations, just add these two equations, I get 2 gamma. Well, it's obvious, right? Look, gamma is an element of is an element of Q adjoin root 2 root 3, right? So that implies that Q adjoin gamma is a subset of. I mean, I haven't given you the complete arguments because we have to run through the fact that gamma is not the only element in there, right? But you can build an arbitrary element in terms of a Q linear combination of powers of gamma. So I'm making this more complicated than it needs to be. This is essentially the point, is once you see these calculations, it implies that root 2 plus root 3 is, in fact, all that we need to adjoin to Q to get everything else. Like if I adjoin the sum of the square root of 2 and the square root of 3, then through field operations, I can obtain the square root of 3 and the square root of 2, which means that this contains that.
Would there be some circumstances where, like where we messed up, where we try to multiply to begin with, where we, other circumstances where we would be messing up more if we tried to add them?
Like, is this special to the square root of 2 and the square root of 3?
Yes.
I don't think so. Like, I think if we have a field of characteristics 0, and we have like f of say alpha beta, I think that is likely this. I was
just curious.
I think we can mock these calculations for like arbitrary alpha and beta. But I haven't, it's been a while since I read through the proof, and the proof of Steinne's theorem is in Galilean. So we were awful close. We just need to add instead of multiply is what all I'm saying, really, last class. Anyway, I have now, of course, gone over time, as is my custom. My apologies. So anyway, and yeah, like I said, for the mission 5, the prime and maximal ideal problem, all of the maximal ideals are all of the prime ideals. There's only, in the finite context, prime, maximal are the same. So anyway, see you after the break.